Michael Levin, the cell whisperer, the synthetic sorcerer, the planarian pioneer, a regenerative revolutionary, and a morphospace magician with a black belt in bioelectricity. Michael is using his knowledge of bioelectric signaling to create living organisms, Xenobots, that exhibit remarkable properties such as self-assembly, locomotion, self-healing, and biodegradability. He is the co-founder of the Institute for Computationally Designed Organisms, the director of the Allen Discovery Center at Tufts University, and an associate faculty member at the Wyss Institute for Biologically Inspired Engineering at Harvard University. With an interdisciplinary approach, Michael has spent over 25 years exploring the frontiers of developmental biology, developing groundbreaking therapies for cancer, birth defects, and other conditions. His discoveries have inspired new approaches to tissue engineering, regenerative medicine, and robotics. In addition to his trailblazing work in the lab, Michael has published over 350 papers and holds numerous patents for his innovations. Dr. Levin has been awarded prestigious honors such as the Scientist of Vision Award for outstanding contributions to the field of vision science in 2015, and the Transformative Research Award from the National Institute of Health for his research on bioelectric signaling in tissue regeneration in 2019. His TED Talk, The Electrical Blueprints That Orchestrate Life, has captivated audiences, and he has appeared on popular YouTube channels such as Lex Fridman and Theories of Everything with Kurt Jaimongal. Welcome, Michael.
Thank you so much. Thanks for having me.
Great. Before we get into the nitty-gritty, you're a synthetic biologist. I'm always interested in the personal side, or at least some personal aspects of the people I'm talking with. So, are there any hobbies that you find particularly enjoyable or fulfilling?
Yeah, I mean, I do a number of things. I spend a lot of time outside, outdoors, thinking, and I do a lot of photography. So I do nature photography, macro photography, things like that.
Yeah.
I kayak, things like that.
I asked Donald Hoffman the same question. He also told me, well, I like amateur photography, and he gave me a link to his Flickr page. Do you post this stuff online or not?
I do. I have a Flickr page.
Oh, great. Can you send me the link afterwards, or I'll send you an email?
I will.
Great.
Sure.
Then I can add it. Okay. So, how did you become interested in this topic, bioelectricity and regenerative medicine? What sparked your curiosity?
Well, believe it or not, it goes very far back. So when I was quite young, probably 4 or 5 years old, I had asthma, and I was born in the Soviet Union. We didn't have access to decent medications, and so one of the few things that you could do at that point was try to keep the child calm, because to keep the airway from constricting, right? And so what my dad used to do is take the back off of this television set. We had this giant television set full of vacuum tubes and whatever. I mean, the front was only, the screen was like this big, but the thing was enormous. And this was 1975, something like that. And he would take the back off, and I would come around. I would look at all this stuff, and I would think, this is amazing that somebody knew how to put all the pieces together in exactly the right way to make the cartoons and everything come out the front end, right? So you see all the wires, all the vacuum tubes, everything. Someone knew how to put all that stuff together. And at the same time, I had a friend, a slightly older kid that we would play outside with, and he was very much into insects and bugs and caterpillars and things like this. And so we would spend a lot of time looking for these things and watching their behavior and so on. And just kind of those two things together, I spent my whole childhood thinking about what they had in common and what was different, right? So who put them together, because they were full of parts too. But unlike the TV, they seem to have a lot of preferences about what happens next. The TV didn't really seem to have much preference, but the insects did. And so there are various transformations, right? The TV was obviously made by people putting it together, but the caterpillar self-assembled from an egg and then somehow turned into a butterfly, and all of these things. And so trying to figure out what they had in common and what was different was something I thought about from a very young age. And eventually, thinking about later on being into electronics and computers and engineering, and thinking about what an amazing use of the electrical dynamics, both in engineering and how we exploit it for computation and so on, and the nervous system, right? Which evolution obviously has done in the brain, and where does that come from? How did brains evolve, and what were all of these electrical things doing before we had brains, right? Both evolutionarily and as embryos. So this kind of stuff I've been thinking about for a really long time.
Oh wow, that is a long time. So you became fascinated when you were very, very young because of these mysteries. It's interesting. There must have been a bunch of people with, at least 1, 2, or 3 people who have had a major influence on the way you think and the way you work, or the way you do your career. Can you name a couple, like 1, 2, or 3?
Yeah. You mean academics? You mean?
Well, honestly, that would be the most obvious one, but it could also be a poet. And if you have a reason why, that would be great too.
Yeah, yeah. Well, I mean, I think pretty obviously, my parents, both in different ways, we spent a lot of time thinking and talking about these various issues, and engineering and science and the role of mind in the physical world. I think I got a lot out of that, actually. And then later on, a lot of people who write books. I mean, you can sort of see back here. This is a small part of my collection of books that I've been collecting and reading since I was quite young, and there are a lot of authors there that were really fundamental in how I think about things, And in bioelectricity in particular, there was a guy named Harold Burr who worked in the 30s and 40s, Harold Saxton Burr, and he was he wrote a really interesting book called The Fields of Life, and then hundreds of papers about he had sort of the earliest good voltmeter that he would go around and take measurements of various biological things, trees and embryos and various kinds of human patients and so on. And so he wrote this amazing book that I think was quite influential in the way I think. And then yeah, just many different authors. And then I had pretty good mentors later in life. Amazing, some amazing people like Cliff Tabin and Mark Mercola and Don Engber, and Len Zahn and people like that, who were kind of those are people I knew in person. But a lot of these authors who write these books that are sort of not quite popular books, but you don't need to be an expert to get a lot out of it. And I owe a lot to all of those people.
Oh, that's great. Almost no single name you just mentioned I've heard of. Then again, I'm not an expert at this, but I wrote a couple down, so at least I'm going to check them out. Is there anyone you could recommend to someone novice like me?
There's a on my website, so I have a resources page on my website that is for other people to try to get into some of these things. And there's a list. There's both a list of books, so there's probably 15 to 20 books that are listed there, that are my favorites for some of these things. And there's there's a page of what I consider my intellectual heroes. So this is another dozen or so people, scientists in the past that I thought were really unique, and some of them are well known, many of them are not well known, but I think they were very profound and very made great contributions to how we think about things. So you can see all of that on our website.
So what advice would you give to students who have an interest in pursuing synthetic biology? What would you advise them?
So yeah, well, one thing I want to kind of back up in this idea. So people have called me a synthetic biologist, and that's not wrong, but I don't really consider myself a synthetic biologist. I mean, my original background is computer science, and since then I've done developmental biology and cell biology and behavioral science and bioengineering and various things. So I don't think I'm necessarily a synthetic biologist. Fundamentally, I still think I'm a computer scientist. It's just that now I study computation and wet kind of squishy stuff, as opposed to traditional silicon and so on. But the advice that I would have to people for students, well, are we talking about practical, sort of practical advice, or are we talking global, sort of big picture, more lifespan stuff?
Probably the latter.
The latter.
Yeah.
So, okay, well, in the more general scheme of things, what I would say is this. um, life is hard, and you need to make sure that all the effort, all the blood, sweat, and tears that you're going to put into something, it's going to go by no matter what. So you're going to put in a lot of effort into something. You want to make sure that whatever you're putting effort into, towards the end, you can look back and say, "Wow, that was worth it. That's what I should have done with it." Right. And so work backwards. So look into the future, and that's hard for young people. It's hard to imagine themselves being older. I mean, I know that, but you make an effort and you sort of imagine yourself being older, and you imagine yourself happy, and you imagine yourself having been productive and proud of what you've done, and then you ask yourself, so what was that, right? Visualize yourself looking back and saying, wow, that's really great. I'm really great. I'm really glad that's how I spent my life. And then you look back and then you ask yourself, okay, so what was I doing? What was that? And the answer to that question, that's what you should be doing. And everything should be aimed at whatever it is that your values are telling you is going to be a worthwhile expenditure of the one resource that you can't get back, which is your time. And so that's one piece of advice I give to my students sometimes. The other thing we talk about is the notion of kind of the notion of feedback and other people's experience. So what I say to them is there's two kinds of feedback that you can get from other people. The very specific stuff, the critiques of specific things you are doing, ways to improve your methods, ways to get better. That stuff is gold, and you should pay very careful attention to that. And you should get as much as you can out of people who know what they're talking about in order to perfect your own craft and improve what you do and improve yourself and so on. But there's another kind of feedback which you also get from equally very successful, very smart people, which is this kind of meta advice about what you should be doing with your life and ways in which you should be thinking about things. And people will say that's not a good way to think about things, or you should go do this, or that kind of stuff, including what I'm telling you now. Right? That's the same kind of thing. These large kind of meta advice. And my comment there is, very smart, very successful people often are really well calibrated on their own ideas and on their own potential and things that they're excited about. They are not necessarily well calibrated on your ideas and what you want to do. And therefore, I don't recommend listening to any of that. Basically, I really benefited in my life from people who had specific things to teach me, critiques of specific things I was doing. That was all. It was gold. It was really important to be able to learn from their experience and improve what I was doing. But at the same time, I would say, with almost without exception, all of the interesting things that I have done and that my lab has done, very smart people told me not to do it. Right. And there's only a couple of people really that, Don Ingber being one of them. There were only a couple of people that were really encouraging of some of the kind of wilder ideas that I had and ways of thinking about things. And so this is my kind of advice to everybody is, take very seriously all the specific things that you can learn from, and pretty much ignore what people are going to say to you as far as what you can do, what you should do. They don't know. Nobody knows. Nobody gets a control experiment in life. You just do what you did, and sometimes things work and sometimes they don't. And maybe you have some insight into your own life and how things are working. It's very rare that somebody has good insight into your life. So you should be the captain of your own ship. Work hard, know what you're talking about, and do whatever it is that you think you should do. And that's it.
I think that's great advice, actually. Just in general, not specific to your field, but in any field. So be careful who you're listening to, where it's coming from. So if it's like a methodology or a technique that can improve your work, definitely listen to those people. But if it's more a general way of what kind of things you should approach, or what kind of questions you should ask, you should listen to your own gut.
Yeah, and your gut on day one is not going to be as good for you as your gut years later, right? So part of the process is to improve your own intuition and to improve your own ability to carve out that path, right, through whatever problem space you're interested in. So you should absolutely listen to anybody whose work you respect. You can analyze and take a look at, okay, how did they get here? How do they think about things? But it doesn't mean that is exactly going to work for you, and you should feel free to modify, discard, innovate, whatever it takes to put your own path forward, because nobody knows what your path should be. Even people who have had a very good path for themselves, they don't necessarily know what your path should be.
If you were to merge your research, let's say in synthetic biology, computer science, bioelectric signaling, with a completely different field like art, music, literature, what kind of hybrid discipline would you create? It's a quirky question, but I'm just curious.
Wow, boy, that's an interesting question. I think. Well, I think some sort of art, I think, would be quite relevant, because one of the interesting things, so fundamentally what I study, right, so my lab does a million different things. We do cancer and AI and birth defects and regeneration and behavioral science and so on. And the thing that ties it all together, why do we do all those things? The thing that ties it all together is my interest in embodied minds. I want to understand, what does it mean to be a coherent being, a coherent sentient being in this physical world. What does that mean? How does it work? And everything else we do is just an example of that, of figuring out, using these various kind of unconventional intelligences in these diverse embodiments of how these beings can exist. And the thing is that we can study sort of in third person. We can study their behavior, we can study physiology, we can do all that. But as people who study consciousness have pointed out, it's extremely difficult, if not impossible, to in third person to understand what their experience of the world is like. Yeah, if in fact, even you and I, being members of the same species and physically similar, it's very difficult for us to understand whether we experience the world in similar ways. And so, one interesting thing is that if you think about what would a workable theory of consciousness output, what would be the predictions of such a theory, right? Normally theories produce numbers and various predictions like that, but that doesn't actually help in this case, because that would be predictions about behavior and physiology. It doesn't help to understand what the first person experience of another being is. And so the only way that I can think of to get around that is something that I think it was Lewis Carroll who said that if you want me to understand what being scared is like, don't describe it, but rather tell me something that's scary, right? And so the idea is that in order to understand what it's like to be another being, what the theory should output is a set of protocols for experiences or sensory kind of inputs that you should receive to be in the same state as them, right? And this is where art comes in. So if I want to, right, so whether that be music or whether that be literature or whatever it's going to be, if we're going to understand each other's kind of primary mental state and experience, the best we can do is produce some sort of input, be it a painting or a piece of music or something else, that puts you and me in the same state. And then we understand what it's like. And so for that reason, I mean, I guess that's a very long-winded way of coming around to the idea that I do think that producing these kinds of pieces that would be considered art are a valuable component of this project of understanding what it's like to be different kinds of intelligence.
I can remember it was a while back. I'm not sure if you're still tweeting it. There were some AI generated images you were tweeting or you're playing with. I'm not sure if it was Midjourney or.
Yeah, it's Midjourney.
It was Midjourney. Yeah. Well, obviously it has to do with the answer you just gave, but is there anything other why you were toying with that?
Well, one thing I found interesting in playing with it is that it's sort of, So for years, for many decades, we've been told to expect that these kinds of artificial intelligences, robotics, computer AI, and so on, would be like these. Um, we had expected them to be very logical, very detail oriented, very specific, and we expected that they would have a really hard time understanding this kind of human gestalt or mood or these kinds of things, right? And so if you look at popular TV kinds of examples. You get back in my day, you had Mr. Spock, and then after that, you had Commander Data on Star Trek, right? And so the idea, so all of these were like these very logical, very mathematical, very precise, but man, they could not understand, what love was all about and this kind of stuff, right? That. And playing with Midjourney is really interesting because it's exactly the opposite. So it gets mood and gestalt very, very well, very well. It produces images that are really good at capturing that kind of thing, but the details it's terrible at the details. So you'll have the wrong number of fingers, and it's impossible to get it to put text down on the paper, and it doesn't understand, it doesn't count objects very well, and things like that. So it's actually the exact opposite. The details it's not good at, but the mood and the gestalt it gets quite well. And some of them, there's also another interesting dynamic here, which is that in order to get these pictures to come up, we prompt it, right? So we write a text prompt that gets it to do something. But a lot of what's happening is actually a feedback loop when it prompts us, because when it produces that picture, the picture it produces is not oftentimes we bring more to interpreting that picture than what's actually in it. So it's kind of this like bi-directional loop, because people will say it didn't really draw that. The reason you think it is because you came up with the fact that this picture represents I don't know, joy or loneliness or whatever you think it represents. That's all in your head, they say, right? And that may well be true, and that's this bi-directional. So you prompt it, and then it outputs something that prompts you to have different thoughts and feelings that may not be directly on the page. But that's the whole point of art, I guess, right? Is to produce something that resonates with the observer in some way, and gets them to have cognitive states that they didn't have before. At least that's what I think art is for.
Interesting. Midjourney is so much better than was the other Dolly, right? I've been subscribed to subreddit. I think it's the Midjourney subreddit, and I'm just blown away by the images. And you say that it's terrible at the details, like text, for example, or an extra finger. I think we're all familiar with the extra finger or the weird row of teeth and stuff like that. But do you think it's a trade-off? Because I was toying with GPT-4, and I saw a YouTube video where they mentioned that it's not very good at math, solving math problems, or very specific math problems. But it's great at the language model is great. And I was wondering, do you think that is a trade-off somehow? Because you see it also in people with neurological defects. They can be idiot savants, for example. So they excel at math or some other very particular niche, but it's always a trade-off for something. For example, they don't look people in the eye, they don't form social relationships. So I think my question is, do you think that's reflected in the AI models we create?
I think at the moment that's probably true, but I don't see any reason why that has to be a permanent limitation. So I fully expect. I mean, look, the space of possible minds is incredibly wide and diverse, and I don't think there's any reason why there aren't other possible minds that are good at both, and in fact, much better than us at both. And so I expect that at some point we will have artificial and hybrid intelligences that are good in both at both the gestalt and the particulars. Right now, this is just this is very early days, and it's all in a particular direction, right? So all of these architectures are kind of grouped, or the AIs that are made today are grouped around a set of tools that people have been using now. But this is just one implementation. There are probably many other ways to do this, and I think we'll find many other ways to do it.
Yeah.
And those ways will and those kinds of and the products of those ways will have very different talents and different failure modes, and they will just be different, yet again different minds.
Well, I wanted to go to the Xenobots, but you mentioned consciousness and well, not consciousness, sentience. What is the most surprising or unexpected connection you've seen between your work and consciousness? And if you could describe or define consciousness, it can be very loose. I'm not very specific, or I'm not gonna hold you too accountable for that.
Yeah. Well, I should say that I actually almost never talk about consciousness in the vast majority of my work, because I think it is a real puzzle. This first person experience that's both the experience and the control, the ability to control what happens next. Um, I think that we can make a huge amount of progress without before tackling that problem. I'm not saying it can be avoided, but I think many things can be tackled without thinking about consciousness at all. And so the vast majority of the work I've done has not been about consciousness. It's been about cognition, problem solving, intelligence, memory, goal directedness. Well, none of those things necessarily involve consciousness. So that's the stuff I usually work on. I mean, with respect to actual consciousness, I think that uh, well, I can say a couple. I can say a couple of things. I mean, first and foremost, I do not have my own sort of novel theory of consciousness. So there's a few of them out there. I don't have a new theory of consciousness for you. Maybe at some point, but I don't have one today.
Do you have a favorite?
But I could. No, I don't think any of them do a great job with what we need. So no. I mean, I think IIT has some things going for it. I don't think it's a complete solution, but I think it's got interesting aspects of it. There are some others that are good, but I think Mark Solm's theory is very good, but I'm not trying to kind of pick or come up with a new theory of consciousness. I can say a couple of things that may be useful, though. One is that if you look at these theories of at the existing theories of consciousness, and you ask, what is it about the brain that they pick out? I mean, why, right? Why are brains conscious? And so they'll say various things, that it's either some people will say it's about the electromagnetic field, and some people will say it's about the quantum events in the microtubules, like Stu Hameroff. Or some people will talk about different kinds of computation that goes on, or different kinds of information processing. The interesting thing is that I'm not aware of any theory that can tell you why it's the brain and not other organs. In other words, all of this stuff, all of the neurotransmitters, the information processing, the electromagnetics, all of this goes on in every part of your body. So if those are the kinds of reasons that you think brains have consciousness, then you ought to take very seriously the possibility that the other components of your body have consciousness too. Now, at this point, most people will say, yeah, but I don't feel my liver being conscious. I mean, that's crazy. I'm only conscious. I don't feel my liver being conscious. But this is a fundamental mistake, because yeah, you don't feel it, and neither do you feel me being conscious, right? The fact that you don't feel other conscious things being conscious, it just means there's a boundary around your own consciousness. And the liver, if it could talk, which it probably cannot, but maybe there are ways to communicate with it. You would find out that actually, yeah, it has, much like your right hemisphere, from which most of us don't hear most of the time, and so on. You might find that, in fact, it has its own consciousness. So I think we have to take very seriously the possibility that, and it's not just because of this kind of wacky idea that I'm laying out. It's also all the people that studied split brain patients, and all the people that study various dissociative states, right, like dissociative identity disorder and all of that. So we already know that we're not as unified as we think we are, and I think we have to take quite seriously the possibility that brains don't have a monopoly on consciousness. The other thing that I'll say about consciousness is that one of the things that makes it difficult to study and perhaps unique, is that all of the other aspects of science you can study in third person, meaning that you you do experiments and you don't change. So when you do chemistry, this is sort of the difference between chemistry and alchemy, right? When you do chemistry, it's entirely third person. You don't change. You do your experiment. You're still the same. You've observed something. Maybe you've learned something, which is an interesting, actually, it's a kind of change. But you can remain the same throughout the experiment. Um, Consciousness isn't like that. If you're studying it in third person, you're probably not studying consciousness. You're most likely you're studying behavior or physiology or something else. But in order to actually study consciousness, you will have to change. And this was, to my understanding, this is what the alchemists were talking about. Is the transformation of the subject of you studying it. So whether that is through various behavioral practices or meditation or psychedelics or whatever it's going to be, to do experiments in consciousness, you're doing experiments on yourself, which means you are not the same coming out as you were going in. And so that's kind of interesting, right? That in order to actually do experiments in this area, you cannot do it exactly in third person the way that we do most of our science. And we still don't really have a great kind of framework for going forward with that.
It's true. We do not have a good framework or methodology to study first-person subjective experiences. I've seen your interview with Lex Fridman, and he asked you about whether you think consciousness starts somewhere like this, or if it slowly builds up. And I vaguely remember you answering that you believe it's a continuum. So it was probably always there in the lowest life form or particles or systems. It just slowly grows bigger, let's say, or more conscious as the system evolves. Is that kind of correct? Is that your opinion on it?
I mean, so yeah. Fundamentally, let's take a step back to things I know more about than consciousness per se, and let's talk about cognition. So cognition, intelligence, those kinds of things. That I absolutely think is a continuum. I do not believe that any benefit is made by trying to use binary categories on these things, and I can tell you why. And so that I think goes all the way to the bottom. I think that even very simple physical systems that people would not consider to be alive already have certain capacities that are the precursors to cognitive processing, and this is active inference and observer object interaction and so on. And so even the very basic physics, kind of at the very bottom, already is on that spectrum. So of course, the very far beginning of that spectrum, but it's already on the spectrum. And so I think that what happens is that life is very good at scaling that up, and the things that are good at scaling that up, that's what we call life, and that's what we define as life. But they're already kind of baked into a lot of the things that go on in this universe. And I would think, though I have no way of demonstrating that the same is true of consciousness. That basically consciousness accompanies cognition, and that at the very kind of the proto the proto-cognitive capacities that very simple systems have already come with some degree of non-neutrality about what happens in next. And this is how we experience consciousness. And so
Okay, so you think that cognition and consciousness are somehow coupled, but if you would make a bet, let's say, would you think that consciousness, that it exists, let's say, independently of physical structures, or that it's necessarily accompanied with cognitive systems, let's say, physical systems?
yeah, that's a really interesting point. I think that I think the answer to that question is the same as the answer to whether certain truths of mathematics exist in an independent manner. So for example, things like the distribution of prime numbers, the various truths of number theory, the different theorems of mathematics. One could argue, and people have, this Platonic sort of Pythagorean view, is that these things exist independently, that even if all the conditions of the universe were different, so at the Big Bang, all the laws of physics were different and things, the universe was completely different, one could argue that all of those things would still be true. And some people, some mathematicians feel that when they do mathematics, they are not inventing new things. They are discovering something that is already there, independent of them. And I think that's true. I mean, I'm no mathematician, but I think that's the way to think about these things. And in the same way, I think the same. I don't want to call it a place, because it's certainly not a place, but from that same realm from which the truths of mathematics are embodied in physical objects in the real world, I think that different types of minds are there as causal structures in the same way that triangles and primes and various other things exist. I think there are kinds of minds that get instantiated in the physical universe when specific kinds of machines, be it biological or non-biological, when those machines appear. So this is extremely speculative. Obviously, this is this is just you ask what my bet is. That's my bet.
Because nobody has the answer as far as I know. So it's a bet, and maybe just a personal preference, let's say.
Yeah. Well, and I'm sorry, could I take about 30 seconds? I need to get up and get a glass of water.
Take your time.
One second. Yeah.
That's fine.
I'll be right back.
We'll wait.
Okay. I'm back.
So if you had the power to instantaneously solve one mystery in the field of consciousness, well, which one would you choose and why?
Well, I think it's the sort of thing where if you I think everything hangs on the word solve, because if you actually solve one thing, I think that means you've already solved many of the other things. But to me, the most interesting thing about consciousness is not the thing that everybody tends to focus on, which is the perception, right? So people talk about qualia and what's it like to experience things and so on, right? That's of course interesting and important, but I'm more interested in the flip side of that, which is the action part. So I'm interested in not the inputs but the outputs. I'm interested in what does it mean to have control, and what does it mean to be a being in the world whose goals, preferences, and thought processes actually influence the physical course of events. So this is what I'm interested in, the experience of being in control, and we can see this with a newborn baby. Figuring out for the first time where the boundary between it and the outside world is. Which things do you have control over? Which things do you not have direct control over? What is your body like? What effectors do you have? Do you have limbs? Do you have tentacles? Do you have wheels? What do you have? We don't know these things coming into the world. We have to discover them, and which is different from how modern AIs and robots are made, right? They're sort of told where the boundaries are, where what their structure is, and so on. So this is the part that I'm interested in, is what is it like to be able to exert will in the world, as opposed to what's it like to have an experience, which I think is what most people in the field focus on.
Right. Okay. Let's go to Xenobots. I think it's a beautiful word. Can you briefly tell us what Xenobots are and what you are doing with them?
Yeah, well, I can tell you what they seem to be, and then I can tell you what I really think they are, which is not as obvious. So what it refers to is some work that was done by in collaboration with Joshua Bongard's lab at the University of Vermont, and Sam Kriegman and his group did all the computer science work for it. Doug Blackiston in my lab did all the biology for it, and so what it is that we were interested in a couple of different things. We were interested in plasticity of cells, and the idea that what is the hardware of a particular species? What kind of behavior is it really capable of in software. So you have cells with a normal frog genome, and the question is, well, what else can those cells make? Could they make something else out of other than the frog? And if so, when they when the embryonic cells of a frog self-assemble into an embryo and a tadpole, um, where do those anatomical and behavioral goals come from? And we tend to think selection, evolution, many years of evolutionary selection. And so the question is, in a novel configuration, what might their goals be if we put them in a different in a different configuration? And so that was part of the interest. And the other part is, can we use AI to help us understand that process and understand the emergence of collective goals from scratch and so on. So what we did in this project was we took some skin cells from an early frog embryo, and we liberated them from the rest of the frog, from the rest of the embryo, and we put them on their own, and we asked a simple question. What will they do in this new environment? Would they reboot their multicellularity and do something different? And so we found out, I mean, there's so you can think about, there's several things they could have done. They could have done nothing. They could have died. They could have walked away from each other, spread out. They could have made a nice flat monolayer like cell culture cells do. They didn't do any of those things. What they in fact did was to come together into this little ball, and then they used the cilia. So cilia are these little hairs that exist on the outside of tadpole skin, and these little hairs turn, and they cause a constant flow of water down the side of the frog, and the mucus. They basically redistribute the mucus along the skin of the frog to keep the pathogens moving and sort of keep them from attaching to the body and so on. And so what they do is they use those cilia to swim. They basically row against the water like you would in a rowboat. They row against the water, and thus this little thing starts to swim. And as soon as I saw this swimming, I immediately thought Xenobot, because Xenopus laevis is the name of the frog that we use, but it's clearly a biorobotics platform, because what it shows us is the ability to exploit the native competencies of these cells as an amazing agential material from which to build biological robots with various degrees of control over what they do.
Sorry.
And so
what do you mean with agential?
So an agential material, what I mean by that is, look, for thousands of years, we've been engineering with passive materials, so wood, metal, Legos. When you engineer with Legos, the question is, what can you depend on them to do when you're not there to micromanage it? Well, for Legos, the only thing you can depend on them to do is to hold their shape. That's it. That's all they do. And wood and brick and things like that, that's all they do. They hold their structure. So you can depend on them to do that. And for thousands of years, we've been building with these passive materials. But now, with the fields of active matter and computational materials, it gets a little more interesting. You've got some materials that do some other things. But in biology, what evolution builds with, and what we as bioengineers build with, is an agential material, meaning that the material you work with is not passive. It has its own agenda. It knows how to do things. It wants to do certain things. And you, as the engineer, don't have a blank slate to work with. What you have is a material that has certain tendencies. So you're not as much of a traditional engineer. You're more of a behavior shaper. You're more of a kind of a trainer. And this is when I explain this to my students, I think about building a tower out of bricks versus out of dogs. So if you build a tower out of bricks, the good news is that it's very easy. You stack them, and they stay where you put them, and that's that. If you try that same strategy out of dogs, it doesn't work, because you stack the dogs one on top of each other, they immediately walk off. That doesn't work. However, if you train the dogs to stay on top, a little circus performance, right? So you train the dogs to stand one on top of each other. Now you've got something interesting, because the brick tower, once you knock it over, that's it. You have to come back and rebuild it. With the dogs, that's not the case. They have an autonomous ability to rebuild. The structure rebuilds. It regenerates, basically. And it regenerates because of the cognitive capacity of its pieces, because you're not dealing with passive bricks. You're dealing with components that are agential. They have an agenda. They prefer various rewards and over punishments, and they know how to do certain things. So I've been working for some years now on this idea, and there are many papers on this now, using the exploiting the agential quality of cells and tissues to make complicated things happen that we have no idea how to micromanage. But we don't need to, because think of how humans train dogs and horses for thousands of years before knowing any neuroscience. You don't need to know anything about what's going on between a dog's ears in order to train him, and in order to have an interesting and functional relationship with a horse or a dog who's going to do things and do it in an intelligent way. You don't need to know any neuroscience. Now, why isn't that amazing? It's because that system offers a remarkable interface to the agential quality of the material. It offers sensory learning and things like that through which you can communicate. Right. So it's more communication. It's more behavior shaping. It's not traditional engineering. And exactly the same thing works with cells and tissues. So evolution does exactly the same. Cells, what evolution is searching in its search space is various ways for cells to hack each other's behavior, because they're not passive. And there's many examples of that I can give you. But that's what I mean by an agential material. And so it's a completely different type of engineering here, that where you exploit. You don't just you don't neglect, and you don't sort of try to paper over, but you actually acknowledge, take advantage of, and maybe even improve the agency of your material, the competencies, the independent competencies of the material you're working with.
Right. So thank you. That's a really great explanation. But I interrupted you when you were speaking about the cilia for the frog cells that were starting to move. So I was curious about that too.
Yeah. So it turns out these Xenobots form this kind of proto-organism that's independent. It swims around. It has some interesting capacities that we're only scratching the surface of. So I'm quite certain we don't know all of the things they can do, but they can do interesting things like, for example, one of the things they can do is, let's think of it this way. We made it impossible for them to reproduce in the normal froggy fashion, because all they are skin. There's no brain, there's no nervous system, there's no reproductive organs, it's just skin. However, within a couple of days, they improvise a new solution to this problem. If you give them loose skin cells in the environment, just sort of sprinkle a bunch of loose skin cells into the dish, what you'll find is that when they run around in circles, they collect those skin cells into little piles. And because those little piles are not passive particles, because they're an agential material, what they do is they become the next generation of Xenobots. And guess what they do? They run around and collect cells to make the next generation, and so on. This is basically von Neumann's dream of a robot that goes around and builds copies of itself from loose materials it finds in the environment, right? So this is just one. I mean, the many other things that they do. And so the idea here is now Josh's lab was creating. They created an AI that helped us to predict and shape the behavior of these guys. And so what you can think about when you say what is a Xenobot, well, the obvious thing to think about is that, well, it's this sort of proto-organism that runs around a dish and does certain things. But that's not actually what I think it is. What I actually think a Xenobot is a composite entity consisting of the four of us, me, Josh, Doug, and Sam, the AI that was involved in making them, and the frog cells themselves.
Interesting.
Because without those things together, this wouldn't exist. The interesting thing is the composite, the observer, the human observers, the AI that helps the human observers to behavior shape the material itself, the genome that went into it, that is typically for making frogs, but in fact it can encode completely different types of behaviors. That's the Xenobot. The Xenobot is the system as a whole, and I think that expanded view of organisms is really critical, because we don't know what the material is capable of until we probe it in various ways. Acorns make oak trees, and frog eggs typically make frogs, and we sort of get lulled into this false sense of robustness, like we understand what this is. This always does one thing. That's what it knows how to do. But that's actually not true at all. They can do many other things that are surprising, but we don't discover that until we probe. So what I really think is that the Xenobot, which is this weird composite entity consisting of different types of beings, is a kind of it's a kind of exploratory vehicle. It lets us. It's almost like a periscope to peer into another world, the latent space of all of the morphologies and behaviors that exist around the typical frog. And there are many interesting puzzles here. For example, when you ask why a certain creature looks or acts the way it does, the answer is always the same. It's, well, evolution and long periods of selection, right? So for eons, it got shaped to be this and that because everything else died out, and so this is what it is now. But there's never been any selection to be a good Xenobot. There's never been any Xenobots. There's never been pressure to be good at being a Xenobot. Where does it come from? And so this ability to do new things, to solve problems in morphological and physiological spaces is something that we're not very good at recognizing. And I see the Xenobot as an exploratory tool, as a vehicle for navigating that space and seeing what else is out there besides your typical standard frog. And that's that's what I think is really critical here. Beyond all the, I mean, of course, there's going to be useful applications, right? We can program these things someday to clean up the environment and to do various things in health and so on. That's just kind of step one. The bigger picture here is that these kinds of synthetic hybrid entities are a set of tools for probing these novel spaces, for probing the space of the possible. Stu Kaufman might say the adjacent possible. What else can this hardware encoded by the frog genome? What else can it do? And why can it do things, given that all the selection was around being a frog? Why can it do those things? And I think that gets back to your very first question, which has to do with this kind of like this Platonic space of forms. I think that there are all kinds of things out there that we don't directly are not aware of, and when we make these machines, whether living or non-living, we get a peek into this latent space of possibilities.
So what's the most significant and unanswered question when it comes to these? Because we haven't introduced one, we still have to introduce a couple of terms. Bioelectric signaling is also one of the things you are working with. The first time I heard it, you were talking about it in such a plain way, and I was thinking, this man is an absolute, he's a genius, and this is paradigm shifting material, and he's just sitting there as if he's talking about what butter he's gonna put on his bread. And it kind of made me chuckle. But so what do you think is the most significant unanswered question related to bioelectric signaling and Xenobots?
Yeah, so we haven't actually merged those two areas yet. We will. We're working on it, but as of right now, the existing Xenobot data, and there's 3 papers on it, don't mention anything about bioelectricity. So we're we haven't put those things together yet. We're obviously going to. Let me talk about bioelectricity for a minute, and we can just kind of talk about what it is. There's a couple of different ways to sneak up on it, but one way, and my goal is to make it sound exactly as mundane as possible, because I want people to understand that this is not some weird controversial poorly understood thing. This is the basis of life, and it's really not as strange as people think about it. And so I think that's important, even though I think that the implications are absolutely huge. But fundamentally, we need to understand that this is not some weird fringe thing. So let's sneak up on it this way. You and I feel like a unified intelligence. So we have goals, we have memories, we have preferences that belong to us and not to any of our parts. If you're a rat learning to get a reward when you press a particular lever, that association, that associative memory that you have between the lever and the reward, doesn't belong to any of the individual cells, because the cells that interacted with the lever on the palms of your feet are not the cells that got the reward, which are in your intestine. They're not the same cells. So how can this rat, what's a rat, right? So there's a bunch, it's a bag of cells, but somehow it has these associative memories that belong to the rat, but not to any of the individual pieces. The same thing for us. We're walking a sort of collection of neurons and other cell types. And so what you're looking for is a kind of cognitive glue. You're looking for something that enables these individual competent pieces, like cells and various other things, to come together to form an emergent large-scale entity, such as a human or a rat, with its own goals, its own memories, and so on, right? So now, in the case of behavior in the three-dimensional world, we know what the cognitive glue is. It's the electrical communication between your neurons. That's what binds these experiences of pressing a lever and getting a reward. What binds it together into an associative memory is this electrical software that runs on the nervous system. And so we already know, this is totally conventional stuff, nothing new here. We already know that electrical signaling in networks of neurons underlies this ability to merge individual cells into a new cognitive being, into a new entity, right? So this is where we start. This is kind of basic neuroscience. So there's no escaping that. Now the interesting thing comes here, and I should say, I'm for sure not the first person to think bioelectricity is important. The first experiments in bioelectricity were made in the 1870s. There were lots of people studying bioelectricity, like Burr and Lionel Jaffe and many other people along the way that made amazing discoveries. So this is something that's been kind of in the wings for a long time. But let's ask, where do brains and neurons come from? This amazing trick of using electrical networks to bind individuals into a global collective, did that really just show up when brains evolved? Because that was relatively recently that we got these big brains. What about what were all these things doing before then? And the reality is that the hardware that brains use to do this, which are ion channel proteins and the electrical synapses and neurotransmitters and all that stuff is ancient. Evolutionarily, it was all in our unicellular ancestors already had all this stuff. So what was it doing before it was used for the brain? And so what we've developed is a view of bioelectricity as a really ancient fundamental cognitive glue that's as old as bacterial biofilms. There's some beautiful work from Garol Soel at UCSD looking at how even bacterial biofilms are using electricity to coordinate all the bacteria toward a common purpose. And what evolution did was basically pivot these electrical networks across different problem spaces. So the first problem space that cells had to solve was the first one was metabolic, and then physiological, and so on. But multicellularly, the first problem space was anatomical. They had to figure out, you start as a single cell, the fertilized egg, and then you have to become whatever type of animal that you are. And to get from here to there, that's a navigational task in this amazing large space of all possible anatomical configurations. And so to make sure you get to the right place, you need to coordinate. All of the cells have to be coordinated towards the same goal, this one path through that morphospace. And so if you ask, what were cells and tissues thinking about before they became brains and neurons, they were thinking about shape. Much like your the electrical activity of your brain spends all of its time thinking about problems in three-dimensional space and also linguistic space nowadays. Long before that, the electrical networks of the body were thinking about how to put together the correct morphological anatomy, and so that's bioelectricity. Bioelectricity is the study of the communication using these electrical signals of different cells that binds them together into a single entity with a single kind of anatomical goal. And what we've been doing in the lab for now 30 years is developing tools, and we developed some of the first tools to read and write the memories of this collective intelligence. So the cells in your body are literally a collective intelligence in exactly the same way that the neurons in your brain are a collective intelligence. And they think about a whole different set of problems. They think about on a different time scale. But we now have the tools to read and write cognitive content into those networks. So we can begin to decode what we can begin to decode what they're thinking, and we can begin to rewrite it. And that's what we've been doing in our regenerative medicine applications.
Would you say that that is a form of communication? Because one of the questions I had was, do you think it's possible to communicate with cells via bioelectric signals?
I think that's sure. I think that's exactly what we do, and to be clear, the reason that this is possible is because that's how our bodies work normally. So cells are communicating with each other electrically, as they are chemically and biomechanically, and that's the only reason we are able to do it is because we hijack that normal interface that they have. So the way cells hack each other's behavior in the body is partly by bioelectrics, and this is why we can hijack it.
Right. So that's very primitive form. Well, it is a form of communication, but I think
Sure.
the spirit of the question would probably rephrase it to, can we speak or talk to cells?
I think the answer is yes, but in the same way that we communicate. So think of communicating with a dog or a horse, right? You're definitely communicating because you can emit signals that are going to change its behavior in a very particular way. So information is definitely passing, right?
Right.
Um, you are not talking the way you talk to yourself or the way you talk to other humans because we have a very particular kind of linguistic encoding that I don't have any evidence that other cells in the body have. So I think that, as far as I know, brains are the only ones that do that particular kind of communication. But there are many other forms of communication that we have with other species that don't talk. Uh, and they're absolutely communication. So yes, you can get information back and forth. You can specify new goals. You can ask questions and get answers. Sure, yeah.
Right. So we have already established that it's not the same kind of communication you and I are having, because that is what brains are doing. So it would seem kind of silly to assume that the cells which make up brains can do the same thing as a brain. That is kind of implied here, right? But what kind of conversations do you think plants and animals would have if they could communicate with each other?
I mean, they do communicate with each other, right? And I'm certainly not a plant ecologist or anything like that, but I think that anybody who studies that kind of thing is going to tell you that there's extremely rich communication between among plants, among animals, and then of course between plants and animals. Ecosystems as networks of communication. I think that's not controversial anymore at this point. I think that's pretty accepted.
Right, but they wouldn't have conversations. They would be passing along information, let's say, but they wouldn't have a meaningful conversation like you and I were having at this moment.
Well, I don't know. What's the distinction? I'm not. I don't follow the distinction. I mean, what's a meaningful? Well, I certainly think they're having meaningful conversations in the sense that the information that they're transmitting is of vital importance to their well-being. So,
Right.
so as much as anything is a meaningful conversation, they are having meaningful conversations. So right. So during predation, during any kind of mutualism or whatever. They or cooperation they are exchanging vital information that's relevant to their survival. So meaning is there. Is it as rich, is it as potentially rich as human communication? I have no idea, maybe not, but I think they definitely are exchanging meaningful, that they're having a meaningful conversation.
Fundamentally, it's not different than what we're doing. Is what you're saying. It's just of different order, different
I don't
kind.
see I don't see I don't Yeah, I don't see where the difference
Good.
would come from.
Uh, if you could, well, if you could send a message to extraterrestrial life, usually people do that by uh, the iron, or what is it, gold plaque, I think, with inscriptions on it, and there have been audio
No, the
messages,
yeah.
right? And I would assume you would have a different approach to trying to communicate to, if they exist, extraterrestrial life.
I mean, I don't know. I don't have a brilliant idea for that, other than to point out that I think humans are um, very, very myopic in how we visualize unconventional other intelligences. I mean, we still argue about whether plants are intelligent and we, various types of animals and so on. I don't think we have a prayer at this point until we really learn the lessons of the field of diverse intelligence. I don't think we have a prayer of imagining, recognizing, or communicating with a truly alien intelligence. I mean, look at how much arguments we've had over plants, over digital AIs. I mean, people cannot wrap their heads around the fact that humans are not the only way to be intelligent and to have a mind. We just find that very difficult. And then I think it's very hard. I mean, there's a few people that are kind of visionaries there, but most people find that very hard. So I don't know. I think there was a science fiction story years ago. I don't remember whose it was, but it was, some alien species finds this what is it, Voyager, I think, that had this plaque on it and so on. And so they find this thing, and it's they're talking about trying to interpret it, this, right? And so they eat it, which is the most obvious way to them of learning about it. And so they sort of taste it, and they're trying. I mean, it's clearly it means something, and it comes from another intelligence. But and so they're kind of they're describing all the tastes that it has and what that means about what the message was, and they basically, if I recall correctly, they basically conclude that this is definitely a declaration of war from whatever the species is, because it tastes really terrible, and it has all these weird elements in it that nobody in their right mind would send such strange elements and so on. Yeah, that sounds about right to me. I mean, the odds that another species would interpret things the same way, I think, is fairly low. But nevertheless, I'm optimistic that if we really commit to the idea that that intelligence can be very diverse and very different from us, I think that at least some forms of intelligence will prove interoperable, and they can communicate together.
Well, you could always rewrite their bioelectrical body plans to write new memory.
If they have bioelectric body plans, right? So, I mean, science fiction is really good for this kind of stuff because it stretches the mind, right? And so, maybe they're patterns of some kind of strong force flow in the nucleus of a neutron star somewhere, right? I think this is Dragon's Egg, I think, was the name of that book. Story, something like that. I
loved it.
Yeah, right. Yeah. So they just even you can't assume anything. The fact that you can't even assume they have chemistry, right? This whole bioelectric thing presumes ion-based chemistry.
Mm-hmm.
You can't assume that they have chemistry. It might be something completely different. I was recently toying with the idea of designing a gravitational synapse. So imagine a synapse that's the size of a solar system. So it's right, and so the point of a synapse is simply this, that certain stimuli coming through change the way that it's going to react to future stimuli. I mean, that's it. It has a certain historicity to it, such that when a certain signals come through, and they change the way that future signals are going to come through. That's the basis of like a medium that can learn and things like that. So you can imagine designing some sort of planetary solar system wide thing that the signals are masses that come flying in. And when the mass flies in, it sort of changes the trajectory of the other masses, that such that the next time something flies in, it does something different. And so and of course, the time scales will be very slow. Spatially, they will be enormous. But I'm pretty sure, and I'm no astrophysicist, but I'm pretty sure that you could design a system like this that functioned as a synapse. You could build various logic gates and maybe neural networks out of it that would be galactic scale, and right. And so, and so that brings up interesting questions. Would we know if we were part of such a system? How would we know? So that I think is what's facing us when we talk about sending messages to other species. Is that kind of disconnect?
This is a super interesting idea. Is it? This is your idea? You should write it, or let someone write a science fiction story about that, because it's very fascinating.
I think it's my idea. I don't remember ever having read anything like that. That doesn't mean that somebody didn't. There's a lot of stuff in sci-fi that people have thought of first. So, but I'm not aware of any of that. I have a lot of ideas like this that would make good sci-fi stories. Unfortunately, I don't really have time to write them, but I toy with that idea from time to time, as writing some of this stuff down. Yeah.
I'm glad that you mentioned this because I had a guest question from T-Car. And it was about a tweet you made, and I think you just touched upon it, or literally explained it, because you tweeted, is there any physics reason that elementary particles cannot be allowed to save state? right? I'll read the rest for the people listening. For example, if you jiggle a proton enough, could there be habituation, sensation, or some kind of historicity to how it responds in the future? I'm not asking if there is evidence for this. If it's already known that particles are trainable, by all means tell me. But assuming not, are there any arguments that if all instances of a particle weren't identical, something well established would break down? Is this forbidden? And you mentioned Sean Carroll. Did that conversation lead to anything?
Yeah, what I was getting at I wasn't even necessarily so much interested in the particles for real. What I was getting at is this idea that people often have kind of philosophical feelings about where memory and cognition should be found. And what I've been pushing is this idea that you can't have armchair preconceptions about this. You have to do experiments. You cannot assume that because something is not a brain or something that looks too simple or whatever, that it's not going to have some of these important properties necessary for intelligence. You have to do experiments. And so, for example, we and other people actually before us too looked at a very simple model of gene interaction networks, just a bunch of genes turning each other on and off. And we found that even that already has 6 different types of learning that it can do, including Pavlovian conditioning. So this is something that's a total surprise. Looking at that system, you would never know that it was trainable until you try to train it. When you try to train it, you find out that, oh, look at this is smarter than we thought it was. And so I wanted to push that to its sort of ultimate limit. And so there's my question. Okay, do we know for sure that electrons and things like that respond to stimuli exactly the same way every single time, that they have absolutely zero trainability? I don't know that I don't think anybody's tried it, but also there could have been, the rest of my question was, well, there might be actually good physics reasons to think that that's not allowed, because if electrons could be trained, that means that multiple particles are actually different, right? That they have different properties, and that may screw up the Pauli exclusion principle or something that is supposed to keep them identical. So I don't know, but and it was interesting. People responded in different ways, right? So some people said, yes, it's impossible because of things like Pauli exclusion, so they have to be interchangeable, or else physics breaks down. Some people said no, it should be possible for various reasons. Some people said this is crazy. Some people said let's try it. Whatever. As usual, I'm not enough of a physicist to know who's right. My goal was just to kind of stretch the envelope a little bit and to point out that these questions are empirical questions. They're not, you can't just have feelings about these things. It's a particle, it's dumb, it's never going to learn. Well, I don't know. I don't know that that's true, right?
It's a great question. So it's so simple, and it's one of these things you assume. It is until someone asks a question about it, and you're like, oh, I always assumed that this was the case. Like, this was this presupposition that I had, and then someone like you asked that. Tikar had a couple of questions for you about this specific tweet. So the first one was your recent tweet about elementary particles saving state and exhibiting historical behavior is fascinating. Could you elaborate on the concept and discuss whether you see any connections to bioelectric signaling, memory storage, or other aspects of your research?
I see. Yeah, I mean, I don't know. If my claim was not that I was expecting to find the explanation for memory, either somatic memory of patterning or behavioral memory of in the brain. I was. It's not that I expect to find that in particles. It's not that I think that individual particles are the basis of memory. Although I'm not saying it's impossible, but I don't have any reason to think that. It was more the broader point of saying that all the way from these sort of planetary solar system scale synapses down to individual particles, nothing is guaranteed to be mindless. We have to do experiments, and we have to ask what kinds of systems are capable of memory, of learning, of generalization, of active inference, all the things that we know are important for intelligence. So I was just trying to stretch people's imagination, really, about thinking about what kind of systems could be tested for stuff like that.
Great. I think he wants to elaborate or add to the question himself. So let me see if that works.
Okay. Hey, Mike, T-Car. So yeah, I was pretty much just giving a nod to your creativity and ability to think outside of the box, and I was fascinated with your thought process on that. So yeah, I understand that it wasn't anything solid, that you were just reaching out across academia and trying to find what other people thought about it. I was a little taken back with Sean's remark to it, which was just, it was pretty much an abrupt no. But yeah, it was just more of a hat tip to you for thinking outside of the box. Can you hear me okay?
Yeah, I can. Yeah, yeah. Thank you. I appreciate it. I hadn't seen. I don't think I saw Sean's response. And the answer might be no. That's fine. I have no commitment to this idea other than if the answer is no, I'd like to understand. There's only two ways for it to be no. One way is it was tried and we know it doesn't work. So that's fantastic. That's a good piece of information if that's true. I'm skeptical that that's what it is, but maybe that's it. And the other way it could be no is there could be very fundamental reasons why, if that were true, other aspects of physics would break down. And so maybe that's what Sean was talking about, which I sort of anticipated that might be the case, although I don't know enough physics to know. And that's also fine. And if that's the case, I'd love to know which principle it would screw up if particles could have states. But that's it's certainly not. I fully expected that. It's possible that the answer is no, but I'd like to know why.
Yeah, exactly. And I think that your line of questioning is beautiful, actually. I mean, you are really being creative and you're considering a lot of stuff that other people have never even thought of. And I think that's really important. I read the residual gravity paper and I thought, well, that is interesting as well. Here's an example of gravitational fields having a memory per se that no one else has really considered before, and that's another indication that there's something else to be eliminated here.
Exactly, and I can certainly imagine that if somebody had asked before that paper came out, if somebody had asked, hey, could empty space be trainable? I'm sure some other people would also reply no, and that would be the end of that. But
Yep.
Yeah.
So while I have you just for a second, I'm not trying to be greedy with your time, but I'm also fascinated with your Midjourney creations and your photography. I mean, this is really great. You got a great eye, your ability to see things that's just really unique, especially with the light in the morning when you're out on your walks. I think it's incredible. Can you tell me what your inspiration is behind all of this?
Well, thank you. I appreciate that. I'm glad. People are getting a kick out of it. Well, my inspiration for the photography is simply that I'm often out in the morning thinking, and I see these amazing things, and I feel like I wanted to share with others and let others see them too. I've never taken a course in photography. I don't really know what I'm doing. I just sort of I don't do any post processing. I don't have any fancy apps for doing anything with these pictures. I basically photograph exactly what I see, and occasionally I have time to. I have way more photos than I ever post. I just don't have time for it. But occasionally I'll put up things that I think are interesting for people to look at, and that's it. I'm just. I'm grateful, and I'm inspired and grateful every day to sort of be alive and be in nature and be able to see these amazing things, and I kind of feel like other people might get a kick out of it too. So that's all that is. And for the Midjourney, I mean, I started playing with it just because like everybody else, I was interested in the new capabilities of AI that were coming out. And sometimes my kids and I play with it together, and sometimes I just have wacky ideas that I think are funny, and then I put them out. It's just fun.
On the Midjourney, one more thing. On the Midjourney, I think it's a little bit deeper than that. You clearly are expressing eukaryotes, the merging of plants and humanity and animals, as well as technology. And I've done a deep dive on you, and it took me a while to understand where you're going with all this stuff, but I think it's totally fascinating. How do you imagine that link, that merge between technology and biology could occur? Do you have any thoughts on that?
Yeah, I think the real merge, is going to occur when we realize that these are not separate to begin with. So I think that it's not two different things that need to be merged. I think we need to be better at understanding this simple thing that underlies it, that underlies both of them. And my framework that I've been working on for this, and it's called TAME, and there's a kind of a monster's size paper on it. In one of the Frontiers journals, where I talk about the spectrum of persuadability, which is a kind of single spectrum on which everything from about simple mechanical systems all the way up through humans and whatever's beyond that. The merger is when we realize that what's not as critical is what you're made of, whether you're squishy protoplasm or whatever engineering materials we use today, or how you got here, which means evolved naturally or designed by other naturally evolved creatures such as us, but actually what your level of cognition is, the size of your cognitive light cone, what spaces that cognitive light cone is expressed in, and how you are able to relate to others. And that covers that basic framework covers everything from traditional engineering to synthetic morphology and regenerative medicine and psychiatry and everything else on the other end. I think it's kind of a common thread. And so to the extent that that's on the right track, I think that's what will do a merger of the fields that are now being separate.
Yeah, that is a massive paper. I believe that you actually posted a more accessible paper or revision of it on Twitter the other day, and I have skimmed through it. I haven't finished it completely. Mike, I just wanted to thank you for entertaining me and sharing your thoughts with me. I'll continue to keep up with you on Twitter. It's been a pleasure to talk to you, sir.
Thank you so much. Really, really appreciate it. Thank you. Yeah,
thanks.
Thank you, man.
Thanks. Jack,
yeah.
Thank you. I'm going to have to run in about a minute. I got to go.
It's okay. Thank you so much for your time. Thank you so much for your answers. You're very, very relaxed guy. I appreciate it enormously, and I really enjoyed it. And I have no reason to be nervous, even though I have sweaty hands right now. So okay.
No reason. No. Thank you for the conversation. It was fun. Thank you.
Thank you. Have a nice day and good luck.